Let's start the seminar. So it's a real pleasure to introduce Graeme Stevens today. Graeme, just a bit of a background. So he's joined the faculty of CSU in 1984, served then as director of the Cooperative Institute for Research in the Atmosphere before becoming director of the Center for Climate Science at NASA, JPL. And since last year, he's also visiting professor here in the Department of Physics in Oxford. It's probably not even necessary to introduce him because he's such a well-known expert on the global hydrological cycle, served as PI of the CloudSat satellite mission based on cloud or spaceborne radar, revolutionizing really our understanding of the global clouds. And now he serves also as co-chair of the Global Energy and Water Exchange Project, GWEX, of the World Climate Research Program. And Graeme is one of these people, he has too many awards and honors to list them, so I won't do it, but he's won multiple gold medals, including Mason Gold Medal of the Royal Meteorological Society. I won't embarrass him much further, maybe just to add that he's also since 2018 a fellow of the Royal Society. But today, Graeme will speak about the color of the Earth, exploring how Earth's albedo and its color basically has evolved over the instrumental record. I'm really looking forward to the talk. Over to you.
Okay, thank you, Philip. I'm going to share my screen now. Hopefully you see it, and I'll go into presentation mode. Okay, you should see my first slide. A comment was made to me about this title, and I do want to sort of make a comment that this was really meant to express an aspect of the physical planet and not really the living planet. And so it really was not meant to make any statement other than the visual appearance of Earth, as you would see it, from example, on this Earthrise from the moon. It is no way is it meant to convey anything else other than that. So I do apologize if someone interprets this in a way that was somewhat more of a statement on a social issue. It wasn't, of course, at all. It's meant to be just a sort of a statement of what Earth really looks like. And so, we talk about Earth as a blue planet, obviously. 97% of the water on Earth is in the oceans, and the oceans cover about 70% of the surface of the Earth. But about 1/1000th of 1% of the water on Earth exists in air, and an even smaller fraction of that tiny portion is spread around Earth in a white veil, thin white veil, which covers about 74% of the Earth's surface. And so Earth equally could be argued to look white as it does blue, and you can sort of see that here in this sort of image. So hence the title of the talk. And this whiteness of the planet is one measure of it is its Earth's albedo. So I'm going to talk a little bit about the Earth's albedo and how over the modern period of the instrumental record, how it appears to have changed and what the factors are with respect to that change. So that's sort of the nub of the talk. I acknowledge a few folks here, like Maria, who actually I invited her on to this seminar because I've stolen a bunch of her work. Seiji Kato's also provided a bunch of stuff, and various model leaders have provided some specific AMIP experiments that I will present some results of, and Andrew Gettleman was one of those providers of the data, so I want to acknowledge those folk as well. They're all contributing in some way. Now, and the other disclaimer of this work is that it's truly work in progress. This is not a final product. I haven't written this yet up. Parts of it exist in draft form, but it's definitely work in progress. Okay, so what I want to do is sort of touch on a couple of topics. I want to give you a brief outline of what the observations about the Earth's albedo are, and put that in the context of Earth's energy imbalance and how we perceive the Earth's energy imbalance to be changing over the last 2 decades of this instrumental record, and whether or not we can actually believe this change that this instrument record seems to suggest. I'm going to talk a little bit about the role of reflected sunlight and its components in this change. I'll talk about a little bit, present some of the results from the AMIP comparisons, and then sort of close with an outlook towards the coming decade. What do we expect? What are the directions of this kind of measurement science for the coming decade? What do we expect? So here's Ray's figure. It's a figure that sort of highlights the bifurcation of Earth's global mean surface temperature. It's created from a zero-dimensional model that Ray published in 2011. I just use this primarily kind of give an idea what the scope of range of Earth's albedo has been over time. And basically this diagram sort of illustrates a sort of a bifurcation between two kind of attractor states, a kind of a complete snowball Earth state and a complete ice freeze state, and the complex nature of the transition of temperature as carbon dioxide expressed through partial pressure carbon dioxide changes over time. On the right scale, more the pertinent to the talk is on the scale on the right, which is sort of the range of albedo of planet Earth over what you might anticipate its history. You might, the sort of the brightest of the planet, it would be in the snowball Earth state, and you know, the estimate of Polk and Ray used a value of 0.6 in the snowball Earth as the albedo of Earth. Others have used a similar value in their paleoclimate modeling studies in the snowball Earth state. The upper end is a purely clear sky Earth. We can estimate the albedo of Earth from our measurements today from a purely clear sky Earth, and that would be about 15%. So if Earth, if there were to completely devoid of, you know, hydrological cycle and clouds, we would think that the Earth in its state with the land masses that it has, the way it's organized, would be about 15%. Present day Earth albedo is about 29%. And the warm state, I've come up with an estimate of the warm state, of a warm state, the state of the Paleocene thermal maximum about 55 million years ago. Come up with an estimate of 0.275. And how I got to that is I just sort of, I sort of was guided by a suggestion or hypothesis of Tapio Schneider, who argues that that state was a state free of maritime low clouds. He has an argument for that. And so basically I've taken the present record and removed the contribution from maritime low clouds, and you get an albedo of about 0.275. So it just sort of underscores the sensitivity of the Earth climate system to these changes in the albedo. But anyway, that's sort of a figures used to sort of give you a range of where we might anticipate the albedo of the planet has changed over its history. Okay, so let me just dwell on a little bit about the observations that I'm going to use. This is primarily an observational study that's been reported here. And the observations, to do that, I'll sort of stand back a little bit and kind of give you a perspective of the observations of Earth's energy balance. And I view this as occurring kind of 4 eras. The eras in terms of, the sort of the capabilities or the philosophy, not so much eras in time, because they're still overlapping. These eras overlap in time. There was an era that was before 1984. I call that pre-Irby era. And that's an era where we try to measure the planet, the energy balance of the planet from what we call wide field of view instruments that were very, very coarse in their spatial resolution. You know, their sort of spatial resolution was really in principle order 10 degrees latitude, longitude. And the main discovery on that era, this was done with kind of more of experimental instruments. There weren't dedicated measurements to Earth's radiation budget. They're more, like, as I said, experimental. The main discovery was we determined that the Earth's albedo was in fact much lower than previously thought. In that era, before these measurements, these experimental measurements, the albedo of the Earth was thought to be 50%. And the satellite observations of that time sort of lowered that down to about the order of about 30%, or the 29% we see today. We struggled mightily at that time to quantify the role of clouds on the ERB. There was much discussion at that time about, do clouds actually increase the amount of energy going back to space, or do they decrease it? Does a reflection from clouds overwhelm the infrared quote-unquote trapping, the infrared absorption and emission with clouds that reduces the emission to space? So does the solar part dominate over the infrared part? So that was a real raging debate at the time. The Irby era started in '94 with Irby, and it's continued even today. And that's basically provided sort of answers to that question. It provided measurements that were finer in spatial resolution with scanning instruments. And we're able to, and we continue that record from Irby through the series today. And we've had sprinkling with scarab measurements in the mid-90s, and on Megatropique, I guess, had the scarab measurement as well. And this will be continued in the latter part of this decade, again, with the mission called Libera. And I'll touch on that at the end of this talk. The main highlights were, as I said, it really kind of gave us an idea of what the clouds were doing to the energy balance, and that in fact, the reflected sunlight actually was larger. The amount of sunlight reflected to space by clouds was larger than was the reduction in the infrared emission to space by clouds. So that was sort of a major finding at that time. And really, in this Irby-like era with series, and with the measurements have been refined and got slightly better, but not fundamentally changed that view. We're now at a point where we're deducing Earth's energy imbalance with top atmospheric fluxes constrained to ocean heat uptake. I'm going to talk a bit about that because that's the data that we're going to use to sort of explore the characteristics of the reflected sunlight and the whiteness of the planet. The third era was an era that's, I would argue, started with GERB, where we're looking at time resolution of the measure of Earth radiation budget rather than spatial resolution, with GERB on the geostationary satellite. And the era that we're about to embark upon is now the spectral era of Earth radiation budget. And I'll touch on that right toward the end of the talk. Okay, so that's sort of the background. The observations that I'm going to sort of report on is from the series EBAF. EBAF is the energy, something it's called balance and field energy. I think it's energy balance and field fields or something like that. I'm trying to find the acronym. Energy balance and field, yeah. So the record's about 20 years now. The record provides top of the atmospheric surface fluxes, 1 degree and monthly sort of resolution. That's the sort of the flavor of EBAF. I'm not going to talk I'm not going to talk at all about how they're created, other than to say, make this important point, and this is quite an important point we're going to come back to, is that these fluxes are derived largely from observation, but there's all sorts of stuff goes into create these monthly fluxes. And once they're constructed, the net balance of the atmosphere of the planet is then constrained to the ocean heat uptake obtained independently from, for example, from Argo in situ measurements of ocean heat change. This is constrained. This is a decadal kind of constraint. It's just an adjustment to the fluxes, so it gives you the energy imbalance as would be implied from the ocean heat uptake. So it's flux measurement constrained over a mean decade of ocean heat uptake. So that's the energy balance and field EBAF fluxes. And I'm going to present these and talk about these and what they show. A brief review of what we've learned about the Earth's energy balance over this modern period of time is that it's sort of shown here in this figure. It's expressed here in terms of the hemispheric energy balances of the planet. To the top left, I don't know where you can see my cursor. Yeah, you can see my cursor there. The top left, you can see the top of the atmospheric fluxes in and out of the planet in the southern hemisphere and the northern hemisphere. What's remarkable, has been noted in a number of studies, is that the reflected sunlight from Earth is essentially identical in each hemisphere, even though the physical composition of the hemispheres themselves, land mass differences and cloud mass differences and so on, are quite different between hemispheres. I'm not going to go through all of these fluxes in terms of time balance, but basically the southern hemisphere is slightly out of balance in terms of its energy flow in and out of the system. It's sort of gaining about 1.5 watts of energy according to the EBAF record, where the northern hemisphere is sort of almost close to balance. And this creates a flow of energy, positive energy, into the southern hemisphere with a net transport across the hemispheres from south to north, largely realized through the oceans. Is about, our best estimate is about 0.4 petawatts of heat going from southern hemisphere to northern hemisphere through the oceans, with some transport of heat from the northern hemisphere atmosphere to the southern hemisphere atmosphere to compensate. And so we get about 0.2 petawatts between the hemisphere, transported between the hemisphere. But the energy balance itself is very close to symmetric. The shortwave part is symmetrical. The long wave part is slightly off by about a watt and a bit. So that's kind of a rather curious characteristic of the Earth itself, is the symmetry, the hemispheric symmetry of its energy balance. With respect to the solar energy balance, symmetry, as I said, the planet reflects about the same amount of energy in each hemisphere, and the same as to the degree that we can measure it or estimate it. Earth system models today don't reproduce this same degree of symmetry. Most of them are within about 4 watts per meter squared, but that implies about 3 times more heat. If you're 4 watts different in terms of the hemispheric balance, it implies about 3 times more heat transport across the crater than we currently observe. So the significance of this asymmetry is probably important, but hasn't really yet been really fully explored or studied. The other point about the symmetry is that while the total energy seems to be the same reflected from the planet, its spectral fingerprints aren't the same. The northern hemisphere, I'll come back to this later when we talk about the Libera measurements that occur in the coming decade, but the northern hemisphere reflects proportionally more sunlight in the longer wavelength, the near infrared parts of the spectrum. And the southern hemisphere reflects like more in the visible part of the spectrum. And this is largely a sort of a fingerprint of the effects of land mass in the northern hemisphere being more reflective in the near infrared, and more clouds in the southern hemisphere, which has a higher reflection in the visible. So then that's sort of some characteristics of EBAF. But let's now go to kind of what the EBAF is telling us about time change over 20 years of the record. And this is the deseasonalized monthly anomaly time series and the trends implied. And these are all statistically significant at, well, in fact, well above the 95% level. And so basically, I just sort of cut to the chase, the net energy into the planet, the net rate of change of energy increase in the planet is, according to this series data record, is changing over time of about 0.4 watts per meter squared per decade. That is the rate, it implies that the rate of warming of the planet is increasing over time, according to this data record. But there are a variety of questions that we might ask with respect to this data record. The other thing I want to make point before I pose these questions is that this change in the net energy into the planet is really strongly basically influenced or really dominated by the change in the solar energy into the planet. The planet's albedo is changing over time, and that's substantially influencing this change of net energy input into the planet over time. But there are a bunch of challenges that we face when we start to contemplate a record like this. The net top of the atmospheric flux, absolute accuracy itself, is plus minus 4 watts per meter squared. So these changes are well below that. So, you know, and just on face value, how could you possibly, accept a trend of this type as being real when the intrinsic measurement of the fluxes themselves, the component fluxes themselves, is large? Well, the argument has been posited several times by the community that the relative uncertainty is much, much smaller, and we're able to track changes over time, not in so much as the absolute itself, but its change over time can be tracked with these with this much greater precision that is implied in the overall accuracy. So is this actually true is a basic question. I'm going to come to this in a second. Is it true? And are we able to use these kind of measurements to actually monitor the Earth's energy input? This is a prevailing question that's going to sort of tax our abilities over time and for the next decade or so. So I'm going to sort of discuss this a little bit. How can we test whether these changes are real? And the simple answer is we don't really have a truly definitive test of the realism of this. We have lots of different ways of looking at it to see that it's consistent with other measures. And that's what I'm going to present you with now, to suggest that this is likely to be, my opinion is likely to be real, but we still have questions to continue to ask of it. Okay, so there's some thoughts on how we might verify the credibility of these changes. I'm still pondering this. It's sort of in progress. I told you this talk was a work in progress. It's sort of a start of a journey, not at the end of the journey. We can start with the sea level budget and the ocean heat content change associated with the sea level budget. You know, for the majority of the heat input into the planet is going into the ocean, something like 90% of that's going in the oceans. I would argue this sort of strong independence, just my qualitative view, that this is probably a strong and somewhat independent way of trying to assess whether this data record has any credibility. So it works like this. From altimetry, we can measure the total sea level rise, and it has two parts. We think of this in two parts: of change due to mass injection in the ocean, such as from sea ice melt, for example, and a change through the thermal expansion through the steric component. And the steric component, of course, is where the heat content information, the change in the steric component over time can be converted to a heat content, and a change in heat content over time is the energy imbalance, is measure of the energy imbalance. The gravity measurements from GRACE provide us a measure of the mass change. So we're able to get an idea of that mass change. And so by combining these measurements and differencing them, you can get an independent measure of the total steric component. And you can then, of course, look at that and compare it to the in situ observations of Argo. Now, Argo is often taken to be the truth in ocean heat content, but in reality, it's a partial measurement of the heat content of the oceans. As we well know, it doesn't really address the deep ocean, and it actually doesn't cover the entire full ocean. So one has to do all sorts of different forms of extrapolation of the less dense measurements of Argo. So the GRACE altimetry is a sort of total measure. The Argo is a less complete measure. And comparing the two gives us some insight, right? And then we may be able to give some insight in terms of the heat content change of the oceans, the energy, and then interpret that in terms of energy imbalance and how that changes, and then compare it to the series time record. A second a way of maybe convincing ourselves that this might be real, or not, as the case may be, is through a kernel reconstruction. And I'd call this moderately strong evidence, sort of still independent. And one can imagine that you can articulate a change in reflected sunlight or change in the energy balance of the planet is sort of considered into two parts, the instantaneous radiative forcing element and an element that's temperature dependent that we call the RX. And the where X we can think of are in terms of the variables that are temperature, that through temperature influence that radiative flux. Temperature, humidity, surface albedo, and cloud are the four elements of this that were considered in this study by Graeme et al. A paper that's in review right now. And so one can, if you have the radiative kernels associated with these variables, one can reconstruct this time series from the radiative kernels, the variability of these, the observed variability of these variables, and then reconstruct the time series. And that's what Graeme basically has done. Now, the purpose of the Graeme study wasn't the verified series record, for example. It was to basically try to estimate the instantaneous radiative forcing. But in so doing, I think that they provide some real insight on this verification. A third example is a comparison to AMIP style experiments where, obviously the Earth system models are forced with the observed SSTs. And what do they produce in terms of trends? Are they similar? This is really no real test. It's kind of a weak test. It's sort of circular, but it's at least in some ways it's sort of a sanity check in some ways, that where if given the observed changes in SST over a period of time, do we get radiative flux changes that are sort of somewhat consistent with what we observe? Okay, so let's sort of just dwell on the first part of this. There's 3 panels here. The global sea level budget is on the left. The implication of that for the ocean heat contents in the middle, and the ocean heat uptake change. The change of the ocean heat content is sort of shown on the right. The dark curve on the left is from the altimetry measurement. So this is over the altimetry record and GRACE record. The mass change from GRACE is in the green curve, as you can see, rising there on the left. The difference between sea level altimetry and GRACE is a measure of the steric component, and that's compared to the Argo observations, which is there in blue. So if the sea level budget was completely closed, you would see that the altimetry mass difference would match the Argo, the heat content, the measurements inferred from Argo. And they do for the most part, except for about 2015, 2016, where they start to depart. And this is, we still don't have, we're still scratching our head really over this. And this is a topic of further research to try and understand, is this real? Is it an artifact of the different data sets? Is it, what is it? But basically, one can see that, you know, for the most part of this record, there's a real amazing agreement between the 2 independent measurements of the steric component. And you can see this more clearly in terms of the heat content in the middle panel here, in terms of the, again, the orange is the difference measurements. Total ocean, this is what actually represents the total ocean heat change. The Argo is what the representation of the total ocean per Argo, which, as we know, is not a complete representation. And the red is the sort of the difference, the residual between the two. And you start to see this residual moving above 0. It's still kind of in the noise of the measurements, so we're still sort of not sure this is how real this is. And then the right panel, I'm going to sort of blow up in the next view graph. The right panel is the ocean heat uptake. It's basically the change of this heat content over time. And it shows you basically the difference measurement in orange. Again, the altimetry GRACE measurement in orange. It shows you the Argo observations in blue, and shows you the series observations of its time series in green. It's sort of shown here more clearly. And here's the trend. This is the watts per meter squared per year, the trend in the energy imbalance from series, again, that 0.6 watts per meter squared, more or less, 0.15 from the Argo GRACE difference. So with the correlation between series and the GRACE difference is about 0.76. The correlation between series and Argo is actually a lot less, 0.3. So the time series correlate somewhat reasonably. The amplitudes are quite different. It sort of gives you a little bit of a warm fuzzy that the series time record is capturing the change. Whether the amplitude's right, we still have to scratch our heads over. But anyway, it's sort of it's not a verification that the series record is right. It's just sort of a suggestion that's may not necessarily be completely wrong. The kernel reconstructions is a study. This is from Graeme's study, and this is really kind of interesting. More needs to be done on this, actually. This is just a sort of beginning of this kind of analysis as Graeme started. Basically, it's shown here you decompose the change in the radiative fluxes over time. This is, I think, is the this is the net flux observed change over time over the series record, almost a 20-year record. They used observational based calculated kernels. It's described in the previous study of Graeme's in 2019 what they've used, but I won't go into the details. But they're kind of, these kernels aren't solely from measurements. They're kind of constrained by observations, so that they try to remove model-based biases that might be in these kernels. And then they use the observed anomalies from either airs or mirror to define the dx factor, And they reconstruct the time series. And this is the reconstructed time series. And I'm just saying, interpreting this reconstructed time series as showing that, you know, the given variability of the Earth system produces changes in radiative fluxes that really do reproduce the series variability in its radiative fluxes. So this is, to me, is yet another sort of indication of the quote unquote validity of the series record. Just an aside, this is the actual instantaneous radiative forcing that they derive for the shortwave clear sky. So this is interpret this as the aerosol forcing. The top panel is what they derive from the combination of series and airs. All the airs observations and so forth to drive the variable X, and this is the inferred aerosol forcing. The middle panel is what they derive using mirror information as input, and then that's compared to the mirror aerosol information that's in the mirror analysis itself. So you can see that they argue in that reconstructing the aerosol forcing from this instantaneous radiative forcing analysis that they're providing. I'm going to come back to this because I'm going to show you what this. I'm going to come back to this aerosol forcing, you know, sort of map in a moment. Okay, third example is the AMIP EEI comparison. They've taken this from Norm Loeb's paper 2019. Basically, this shows 7 AMIP style runs. You know, the AMIP experiments had to be extended beyond the CMIP 6 in order to extend it into this longer period of series. So these were special runs. I know Andrew was involved in this study and provided these data, and we've used some of these data in my own analysis. I'm still in the process of analyzing the model results. I've got through analysis of 4 of the 7 models, so it's still in progress. So what you'll see is results from 4 models. But anyway, so they find a similarity in terms of the AMIP models reproducing to a large extent the observed variability and trends that are observed in the series data. I'm not saying this is anyway a verification. It's just, you know, it's an interesting sort of comparison. Okay, so this is my sort of takeaway, and we can debate this and argue this actually. The tests so far suggest that the changes observed apparently consistent from these multiple perspectives. It's somewhat consistent with these multiple perspectives. I think the kernel analysis is really revealing. And so we might consider that these changes we're observing and shown here on the left are real. This is a topic of much more work and debate over the coming years we needed. You can't just necessarily accept them as face value, but I'm going to accept these now at face value, despite what I just said. And if they're real, then we've seen that they are really strongly influenced by, governed by changes in reflected sunlight, and hence the whiteness of the planet. The question is then, what are the factors responsible for the changes observed? Are they low cloud changes, like Norm was arguing in his paper 2009? What about surface changes that occurred, like snow cover and sea ice changes that have occurred over the last 2 decades? What role have they played, for example? And so these are the sorts of questions I'm now going to try to answer through an analysis procedure that I introduced back in a paper I wrote in 2015. But this analysis procedure isn't kind of new. I mean, Donahue had done something similar in a paper before this, and Taylor had done a composition analysis even before that. So it's kind of not entirely new, but my approach was slightly different and drawn from a kind of a sort of a radiative transport model. And the simple model is shown there. You suppose the atmosphere is just one layer that scatters and transmits sunlight. And then basically one can express the albedo of the planet in terms of reflection from the atmosphere itself, and that's that little r, and the contribution from the surface, which is this second factor I'm showing here, which is all the mobile scattering between the atmosphere and surface that takes place. And this component is the surface contribution to any change observed or the reflected sunlight observed at the top of the atmosphere. So my analysis, what I'm going to do is, unlike what I did in 2015, I'm going to look at the changes in these over the series record. What's contributing to the change in reflected sunlight? Is it coming from the atmosphere? Is it coming from the surface? And so on. And so basically one is able to infer these component parts, these individual component parts, by knowing the fluxes in and out of the top of the atmosphere and in and out of the surface. We know what these energy fluxes are, which we have from a series data record. We can basically invert this simple model and come up with these estimates of these component parts to the sunlight reflected by the planet. The component parts, again, are a part due to the atmosphere itself and a part due to that which comes from the surface, modulated by the atmosphere as it goes through. So I'm going to apply these to the series time series, and I apply these to the AOPP model experiments, and look more at the trends. I'm going to present these as trends. And that's so, as I said, this is sort of work in progress. The presentation of this might not be kind of optimal in terms of presenting these trends, but I'm just sort of doing it in a simple, quick way that I created these histograms to look at these trends. And so this is sort of a breakdown. The open bars are the all sky, that's cloud and clear, and the shaded are the clear sky components, you know, how the clear sky breaks down. You can see the red highlighted is, I call it the atmospheric all, that's the reflection by the atmosphere. That's just the scattering that's taken place by the atmosphere, sending sunlight back to space. The surface all is that bit from the surface with all of the mobile scatterings and so on, attenuated by the atmosphere, through the atmosphere, back up to the top of the atmosphere. So the surface all is a contribution to the top of the atmospheric flux by the surface, okay? If the surface albedo alpha was 0, you would have no contribution, of course. And then there's the equivalent clear sky components of this. Okay, so there are a number of actually interesting things that come out of this. Is that the points to note are the shortwave trend that we observe from this record is entirely driven by atmospheric influences on shortwave fluxes, right? It's essentially the atmosphere, and the change of the atmosphere is driving these trends in shortwave that we see. The surface contribution to the top atmospheric flux is essentially negligible. So the changes in sea ice, the change in snow cover land and so forth, having no real net effect on the change in the sunlight reflected by a planet over this period. And so the question is, that's rather, and I put a question, the question mark there is that questionable? It's good. Why would that be the case? So I'm going to sort of explain a little bit that, and to some extent, this next breakdown sort of shows this. The other thing is that the clear sky change in reflection by the atmosphere, clear sky change by the atmosphere is about half of the total atmospheric change. So about half of this atmospheric change, you'll see in a minute, is from clouds, and the other half's from the clear sky change. Okay, so you go see it here. There's the atmospheric all sky. There's the cloud radiative effect. That's the cloudy contribution to this trend. So the cloud contribution over 20 years have changed. The clouds have changed in such a way as to decrease the amount of sunlight reflected to the planet, from the planet, I should say. The clear sky change has occurred here as well. Atmospheric clear sky. And then these are the surface flux, and this is something I want to kind of sort of talk a little bit about, and why the surface contribution is so small. This is the change in the flux at the surface itself. So indeed, you know, the changes are taking place at the surface. It's changed the amount of sunlight reflected off the surface. It's decreased. That sunlight has decreased reflection off the surface. You know, less snow cover, reduced sea ice, for example, will change the amount of flux reflected off that surface. But what gets transferred to the top of the atmosphere is essentially reduced by essentially a factor of 10, which is this ratio here. This is a sort of a measure of the bulk transmission from the surface to the atmosphere, and reduces this change by a factor of 10. So the atmosphere strongly modulates or buffers the changes that we see at the surface. So the atmospheric trend, the dominant part of the observed trend, is equally composed of trends from this clear sky and from clouds. The surface flux trends are attenuated by atmospheric processes, reducing influence top of the atmosphere by about a factor of 10. And this is sort of a measure, this ratio is sort of a measure of the bulk transmission of sunlight from the surface to through the top of the atmosphere. This is what that transmission, quote unquote, looks like for all sky and clear sky. So you can basically, the essential point is that the influences of surface changes on top of atmospheric fluxes being highly attenuated, but these influences are most pronounced at the higher latitudes, where the surface changes are perhaps most acute. So the system buffers really acts to buffer strongly effects occurring at the surface through the atmospheric changes. This is the sort of the distribution of change of the trends. These are trends, maps of them. All sky, atmospheric all sky. This is the cloud radiative effect. This is the clear sky change. The clear sky change. This clear sky change, I just showed the aerosol forcing inferred from the Graeme study. You can kind of see similarities with respect to the forcing, which is in the warm colors, and the change associated with the aerosol here shown here in the dark colors. Well, interpreted to be aerosol. Actually, the clear sky change needs much more deeper dive to understand what's really driving that in this data record. It looks perhaps to be mostly aerosol, could only be mostly aerosol. Water vapor changes over this period of time is about 15% of the total all sky change. So it can't explain the observed large clear sky change, shall we say. Okay, so here's a summary of what the observations show, if you believe them. Okay, there's a trend in the EEI over the modern period of about 0.4 watts per meter squared per decade. This EEI trend is largely defined by changes to solar radiation. This change reflection is almost entirely a result of change in scattering by the atmosphere. Surface effects being almost entirely buffered by the atmosphere. The atmospheric scattering change over time is almost equally divided between cloudy and clear sky contributions. Let's now look at the model comparisons. As with Loeb, he had 7 of these AOPP experiments run extended to 2018. There's 6 models. I have 6 models. I'm still analysis still in progress. As I said, I've only got to 4 of these. And this is kind of a dense figure, and it's just sort of thrown the same format. So let me just sort of work my way through this. You can see to the left is the total shortwave trend, the series trend observed, and the 4 models I've analyzed so far. There's a surface contribution, all small from the models, somewhat larger than observed, but nevertheless all small models compared to the overall trend. The top of the atmosphere contribution from the atmosphere shown here in this center panel. The clear sky contribution shown here in the bottom, and the cloudy sky contribution shown here to the right. This cloudy sky contribution, one could maybe sort of suggest this is a sort of a measure of cloud feedback. So it's a change in cloud over the time period with a given change in the surface temperatures that have occurred. So you could use this as some way of testing, evaluating cloud feedback in these models in the Earth system. So the couple of nodal points one can stare at this for some time. The 4 models analysed so far do indeed produce the negative trends, as Norm Loeb had indicated, obviously, in his paper. So really just to reconfirming that, there's nothing new actually. The models and observed surface contributions all tend to be small. So similarly, models tend to show that any changes in the surface that are built into the model are also muted or small. The contribution from the atmosphere dominates both model and observed trends. So that's something that's consistent, of course. The atmospheric contribution is almost entirely from clouds in the models, in contrast to what we observe. So the driving force in the models of the cloud changes. Models capture the sense of change in the clouds, of course, as we sort of indicate over here to the right, if not in magnitude, but perhaps not in magnitude. The CESM has a kind of a very strong cloud feedback, it appears, compared to the other models. But these models are essentially predicting this sort of positive feedback, as it were, into the system in that reduction in clouds, reducing the reflected sunlight. So the fact that the clear sky contribution is much smaller than models is probably reflective of the type of aerosol forcing that's gone into these AOPP experiments, not necessarily being as large a reduction in the aerosol over this 20-year period that would imply from the observations that show this reduction in scattering by aerosol over the series record. Okay, so that's sort of the analysis of the series data and what it's telling us today. Now I want to just sort of touch on last couple of view graphs on kind of what the outlook is, what the sort of thinking and the philosophy is going forward in terms of trying to grapple with questions about the Earth's energy imbalance and maintaining records, data records, and so on. The Earth energy imbalance, there's assessment going on. It's a sort of a large, it's an international effort to sort of ask the question, how well do we really know the planet's energy imbalance? I'm kind of giving you a hint at the answer to this. We think we understand that the energy imbalance is changing over time, but we still are grappling with basic questions about how well we really know this. I think we have to question, we can't just necessarily blindly say, well, we know it because we have Argo. That's far from the truth. Ongoing efforts will continue to preoccupy the community on this very issue. It's going to be a focus of the WCAP in the coming decade, is the Earth energy imbalance. Continuing the series-like record is something is important to do and is planned for, and the Libera mission circa 2027 is intended to do that. And there is a definite move taking place towards more spectral measurements of Earth's energy imbalance. And this is a way, it opens the way to really dig in and be more process-centric in terms of trying to understand energy balance and imbalance changes. Just a few words on Libera. It's a newly selected Earth radiation budget measurement. It was selected in 2020 by NASA. It's a measurement program that's led through LASP. The PI is Peter Paluski. Maria, who's on this, attending this seminar, is a deputy PI of this. It's so named because obviously it's the daughter of Ceres. And so in some ways, symbolically, it's a continuation of Ceres and the daughter of Ceres. The objectives of this were a number of objectives. One, of course, was fundamentally and seamlessly to continue the data record, the 20-year data record, and continue it on for the next decade. So that's sort of good news for our science. The sort of other key aspect of this is that it was an attempt to demonstrate and really change the paradigm in terms of making these measurements into a much more affordable, smaller instrument, more affordable strategy to be sustained for continuity. So it's introduced new technology to make this a more affordable way forward to make Earth radiation budget measurements. And then the third part of this was that there was it's nudging its way ever so slowly and in a small way into some spectral measurements, and it has a split shortwave channel to measure the Viz versus the shortwave near IR fluxes and contrasts. And the reason we want to do that is that I'll touch it. Well, I guess I'll touch it now. I already showed you this figure about showing the spectral nature of reflected sunlight, and that the fingerprints of the spectral characteristics are there's fingerprints of these processes that shape the fluxes coming out of the planet are contained in spectra. And this is an interesting plot. It's come from analysis that Maria's doing. It's under construction. It's from simulations from HADGEM, where we've taken the HADGEM fluxes simulated. I guess it's sort of, I don't know whether it's AMIP style runs. I think they're AMIP style runs, and considered the reflected flux from HADGEM in its visible and near infrared portions. And it's shown here, the differences between northern hemisphere and southern hemisphere of the ratio of near infrared and vis. So positive values of this ratio suggests that the near infrared is larger in the northern hemisphere than southern hemisphere, and vice versa. And so quite interesting, you can see here how, as we said before, how in the clear sky landmass of the northern hemisphere really sort of glows here in terms of the near infrared. The near infrared flux is much larger than the southern hemisphere counterpart, just because the landmass is more reflected in near infrared. Conversely, of course, the cloud radiative effect has a much reduced near infrared, or the southern hemisphere has more cloud reflecting more in the visible. So the ratio, the proportion ratio between near infrared and visible is reduced with the clouds, because there's more clouds in the southern hemisphere and they reflect more in the visible. And so these two factors conspire to kind of cancel to some degree, giving you a ratio that's more neutral in terms of the combination of these two factors. But you can see that just by making these measurements, you can see surface process influence on the reflected energy, i.e. as shown in the black curve, and cloud process influences on the reflected sunlight, i.e. shown in the orange curve. And they really separate out spectrally like this. And so this is one of the sort of the underlying motivations that make sort of bulk measurements that are more spectral in nature. The future of Earth OBS and Earth radiation budget is spectral. It's right at our doorstep. It begins probably with pre-fire, which is a measurement strategy to measure the spectral OLR. It's actually doing this with CubeSats, would you believe, making spectral measurements of OLR in 60 different spectral channels. It continues or overlaps with Clario Pathfinder and then Truth at some point. I don't know exactly the timeline for Truth, but these are the spectrally resolved solar radiation measurements. Their objective is somewhat more of a calibration laboratory in space for other measurements, but nevertheless, they're making these spectral measurements of sunlight, of the sunlight. And then at the end of the decade, we have what's called an aerosol cloud convection precipitation mission or program concept. That's a multiple satellite concept that seeks to get measurements of the Earth's radiation budget down to the kilometre scale, down at the process level scale where clouds and aerosol processes couple and interact. I don't think I'm going to go over this on the time. I'm going to skip over that. So I'm just going to sort of now jump to the summary and come back and discuss this if anyone's really interested in it. Let's just summarise. We've got these little thumbnails sort of on the left there to sort of highlight the topics of these bullets. Quantifying Earth's energy imbalance is and remains a challenge. We haven't yet established the methods that can deliver an Earth energy imbalance to a notional requirement of about plus or minus 0.3 watts per meter squared. This is a notional requirement that was discussed in this review of the EEI by Messenyak et al. In 2019. The suggestion of series independently verified, I use verified sort of in quote unquote, it's sort of somewhat maybe with tongue in cheek, but as best as we can do at the time, is that there is an increase in EEI over the past 2 decades. This implies an acceleration of the warming of Earth over this period of time. The energy imbalance trend is largely defined and perhaps controlled by changes to solar radiation reflected by the planet. The changes are entirely from atmospheric influences, with surface effect being strongly buffered by the atmosphere itself. The changes are equally split between cloud and aerosol changes in the record. Models reproduce gross features of these changes, that is, they have the right sign of the change, for example, the right sense of cloud feedback, but the magnitudes of changes and implied feedbacks can differ significantly from that observed. Models fail to reproduce the observed clear sky change, aerosol-based, we think. Characters change, however, needs more research and verification, and it's not surprising that models don't actually capture this because it's really going to be dictated by the assumptions they make about the aerosol forcing that's going into it. Plans are underway to extend the current record into the next decade with an evolving focus on spectral. The ACCP, which I just really skipped over because of time, ACCP represents a shifting capability to deliver processes at the kilometre scale. It's still going to do this with high spectral resolution, and much work in the coming years will be directed to advance this capability. Basically go after ways of really constraining radiation kernels, for example, from the observations. So that's kind of it in a nutshell, and I will hand it over now to questions. And I have no idea what the time is because I didn't have my watch on me, and I should have done that.
You're perfectly on time. It's great. Well, thanks a lot, Graeme, for a really fascinating talk. There's lots of questions come to my own mind, but I'll refrain. I think the first one who had a hand up was Tim. Tim, do you want to just unmute?
Tim, can I stop? Stop sharing, or do I need to share? Continue to share.
You can stop sharing, probably.
Okay, thanks.
Great, thanks, Graeme. That was a great talk, as usual. Just as a sort of slight outsider in this field, I mean, you know, you were sort of commenting on the fact that these results might be consistent with positive cloud feedbacks, which, of course, is a kind of mega result if it's true, because, you know, as we all know, that's the biggest of the uncertainties in climate change research. But it wasn't quite clear to me. I mean, for example, you didn't talk much about, you know, what people call indirect aerosol effects on clouds, and the fact that maybe as we decrease the amount of aerosols in the atmosphere, the sort of brightness of clouds also decrease. So I guess that's my question. Is this the effect of humans on aerosol amount, or is it the effect of humans on greenhouse gases? Because that's a sort of $1 trillion question, isn't it?
Yeah. Well, I don't think these data can really, I'm not quite sure these data can really peel apart aerosol indirect effects on clouds, for example. They're kind of still fairly bulk in what they can represent. But I think what you are seeing the human influences on the aerosol and the reduction in aerosol and reduction in sunlight reflected over the 20 years. It presumably is related to reduction in aerosol, but again, that needs to be further delved into. As I said, this is kind of work in progress. With respect to the cloud feedback, now, I've used feedback sort of loosely in the sense that, again, these are AMIP-driven experiments that they can compare the obs to. The natural world is showing signs of these feedbacks. The model in these AMIP experiments are probably not feedback per se, because they're driven by fixed SSTs and there's not the feedback going on, coupling going on. But I do think this is one of the reasons why these observation records are important to sort of dig into and determine that they're real or they're credible or not, because they will give us insights or constraints on measures of the overall feedback of clouds, like I just said. And that's, again, a topic that I think we want to dig into much more deeply than these trends in the Earth energy balance. This is kind of new, and we're just sort of beginning to grapple with the credibility of those. Once we think they're credible, then we can start really delving into these sorts of questions that you're asking. I'm not quite sure they'd have the resolution to do the aerosol cloud interaction. We may be able to do that by looking at regions where we know aerosol and cloud interactions are quite pronounced, like off the coast of China, for example. But, you know, that's something we might be able to explore further.
Okay, thank you very much.
Thanks, Tim. You asked my question anyway, so that's perfect. The next one is Duncan, and then Ray.
Thanks, Graeme. Excellent talk. Tim also took my question, but I'll kind of.
You don't have to ask it then again, you know.
Oh, well, I have a related one. So it was interesting. It's interesting to note that the contribution from the clear sky, you saw a smaller contribution from the cloudy sky. So if it was all aerosol, then you would anticipate there would be at least as much from the clouds as there was from the clear sky. What I was interested in, though, was what this implies for the and then just build on Tim's point as well, what this implies for ECS and the models which in CMIP6 showed a high ECS. CSM2, I think, was one of those, and this series data matched pretty well with that. Does this rate of warming imply or corroborate those models which show a kind of increased warming later in the century?
I'm not sure I can really say that, but you know, the cloud feedbacks, or the way the clouds change in the models versus the obs, they're quite similar, in fact. So I mean, it does lend credence to that. But I do know that there are studies that have gone to point to the Southern Ocean clouds and the role they've played in terms of defining the high values of ECS. They don't show up so much in these trends over the time, over these 20-year records. But primarily, you saw the cloud changes were primarily subtropical low clouds and tropical convection is where the big signatures of the cloud effects are showing up in this data record, less so the Southern Ocean clouds. But there have been a number of studies you're probably aware of that where this point to the Southern Ocean clouds is the culprit for the high ECS. So I'm not sure what it tells us about, you know, the climate sensitivity of models yet. That's part of the next step in this. This, as I said, this is a beginning of a journey rather than getting there. So I think that's the sort of question you want to ask. You know, what does it tell us about cloud feedback, for example? That's something we'll dig much deeper into again. This is just fairly cursory at the moment, what I've shown you. So yeah, I mean, these are all kind of neat topics to explore. Whether we can say much about the aerosol cloud interaction with in this bulk energy balance sense is something again we want to look at, but I'm not convinced we can say that much. But you know, that's my take.
Thank you.
Great, Ray.
Ray. So you mentioned the Donohoe paper, Aaron's paper, and you know, something I mildly disliked about that paper is that in some places they almost seem to be saying that the Earth is warming because of the change in albedo, because of the short wave, not because of the long wave. Whereas I think what's really happening, and the paper has actually been misinterpreted that way. Whereas I take it, you know, my view is that what's really happening is that CO2 is going up. That reduces the OLR. The system hasn't completely equilibrated because the ocean is still warming up. But then you've got some mixture of externally imposed aerosol forcing and cloud feedbacks that are amplifying things. And right. Is that your take on this? What
you're seeing in these trends are those amplifying factors in the trends. The overall warming itself is, you know, undeniably through the greenhouse gas buildup. This is just how that in turn gets amplified. So what we're seeing is that warming is increasing over time through this amplification that's occurring through sunlight changes taking place, feedbacks associated with sunlight changes. That's how I interpret this.
Okay, good. Yeah, I just wanted to make sure we had the same picture of what's really going on. Yeah. The second question is what the future missions that you mentioned. Is there a prospect that they will actually increase the absolute accuracy of our measurement of the Earth radiation budget down to that 0.3 or plus or minus 0.3?
This is our real dilemma. You're not going to get there radiometrically. So you know, we can put all of the series in the world up there. You're still not going to get down there. Argo, you're going to have to sort of populate the world's oceans and with deep Argo everywhere to get there. We have ideas about how we can get there with a totally different measurement strategy by measuring photon momentum. And you do that by measuring accelerations on spacecraft due to photon flux momentum. And we can measure acceleration of spacecraft so exquisitely accurately now with these accelerometers have been developed for like GRACE and so on, that we can do that way more accurately on paper than we can do radiometrically. And so we have concepts to try to move forward with this, with basically using, you know, spherical satellites being pounded by photon flux orthogonal to their direction of drag, so the drag doesn't play a role. And so, you know, you can actually pull apart this component more accurately in principle. And that's what we're beginning to look at. You just can't get there radiometrically. I'm not sure we can get there. Even in situ, even the oceans are only 90% of the total change, right? So you're not measuring the total change. So it is out there to be a challenge in front of us to be thinking about. How are we going to get the meaningful measure of this for our planet?
That's great, thanks. I'm going to have to leave and go to a Habitable Worlds conference now, but it's been great listening to you. Yeah,
you're right.
Great. The next question is by Miles, but I'll sneak in one quickly in between follow-up question on Ray's question. How important is the diurnal correction in this uncertainty? Because that must make a big difference, that you have just not a proper sampling of the Earth. Do you have a good sense of that?
Well, that's, I mean, I think there's a lot of questions we should be asking the data record like this. So, for example, you know, Sirius does have a quote-unquote diurnal model, uses geostationary observations and casts some black magic on those and uses that to do the diurnal, you know, diurnal time averaging. Is this disturbed? Is this contributing to the observed trend? If it was artificial, if that trend was artificial, you wouldn't start to see the consistency like you're seeing in these other, coming from these other directions. So I suspect it's a factor. It's probably not distorting the trend, but you know, that's again the sort of thing we need to dig into and convince ourselves of that. You know, we should be asking these questions all the time, not just using the observations as if they're real. Ask the questions about how can we convince ourselves they are real. You know, so I don't have a simple answer, but I expect that there's probably not a driving factor in what we're seeing.
Okay.
Otherwise, you wouldn't be able to reproduce, for example, these kernel analysis. You wouldn't be able to reconstruct the time series so exquisitely like they do. I mean, that was pretty surprising to me that they were able to get anywhere near the time series that was observed. Anyway, that's just my take.
Great. I think the last question probably goes to Miles.
Miles?
Thanks. Great talk. And it's less of a question because we're going to be getting on to talk about this with Stuart in a minute anyway. But
yeah.
I mean, I hope you're engaged with AR6 reviewing at least, because
I did review AR6 and I was pretty critical of certain things, particularly when it goes to EEI. I think they made some statements about EEI that just aren't real, you know. But anyway, that was my
okay. Yep. Great. I mean, but I mean, it's interesting just to flag that, you know, if you look at the central estimates of the current rate of warming that are implied, at least by AR6 conclusions, it's gone. You know, IPCC are essentially taking it as fact that the rate of warming has accelerated by 50% between, you know, the sort of 1980s to 2000s and what it's doing at the moment. And this is, a lot of this is what's this acceleration, which is kind of going through as IPCC fact of these days.
Yeah. See, that's a bit of a worry.
I mean, that's why. So, I mean, you're presenting it as, oh, this could be happening, and this is interesting.
Yeah, exactly.
But it's you know, within a few months, this may be IPCC dogma. So I think it is. We'll be talking about this again in a minute, but I think it's incredibly important for us as a community to really get onto this, because, you know, this is a testable prediction. You know, we're going to be at 2030 before we know it, and if we've predicted, anyway, sorry,
I hear you.
I'm
totally with you on that. You know, the observations are suggestive, but there's a lot of questions about the observations. You just can't just take them as fact. And I really do think that the chapter that I reviewed, they overstepped their bounds in what they claim for. They overstepped their bounds in what they deemed was certain.
When your predictions start being recycled by Alexandria Ocasio-Cortez, you know you're in trouble.
Yeah. Well, yeah. Okay. Well, yeah. Okay.
Off that.
On that note, it's probably a good time to draw this to a conclusion. So thank you very much, Graeme, again, for a really fascinating talk. Really great insights, nice overview of the state of science. Maybe last advertising jingle. It's nice you mentioned pre-fire. Some of the pre-fire instrument components are being built
it's Oxford.
AOPP.
Oh yeah, of course. There's an Oxford flavor in them. Yeah, for sure. Yeah, exactly.
So there's some of these things are all coming together, which is really nice to see.
Yeah,
so thanks a lot for your talk, and thanks to everyone for joining.
Yep. Thanks, guys.